small errors in the estimation of the CR position. And as I said, it's in a way representing the tooth or the group of teeth in a single point. At this point, we are interested to know the force direction. So is this force is oriented like this? Is the force oriented like this? Anyway, the moment direction, so like this or like this. And very important, the MF ratio. So which is the ratio between the moment, sorry, I have to turn this, otherwise, between the moment here and the force. And the moment of force ratio is a distance actually, because in fact the force is expressed in maybe in gram, and the moment is expressed in gram millimeters. Sorry, I'm not in a good position for drawing this here. Sorry. So the force is expressed in gram. The moment is expressed in gram millimeter, and a moment of force becomes a distance, which in our environment are millimeters. And the moment to force ratio is a value that is used in engineering. And when they design how to make a bridge, they are talking about the moment of force of meters, or maybe even a scale even larger. For us, we talk about millimeters. Okay, so again, we need to know the force, the moment, and the ratio between these two. Once we know these three things, we have what we call a qualitative force system, which does not include the absolute magnitude of these two vectors. And that's what we're looking for, a qualitative force system. We have to relate this qualitative force system to any possible dental movement. So, let's start to describe a little bit the movement. It's very often that I see in books definition of the movements that are very limited to a few examples, but the reality is that the movements that we meet are an infinite number. So we cannot make, a few examples, a few categories, and apply the force system to this category. We have to define a system to describe mathematically every single movement or path, better said. So you have ever, I'm sure you have heard speaking about translation, about rotation, and maybe combined movements. So let's describe them. What is a translation? A translation is a movement, or let's say is a kind of movement, where all points of a rigid body, in our case our tooth or a group of teeth which is solidized together, are moving along parallel paths. So all this that you see, and it's only one plane, are different in translation. So translation is not one movement. All this you see here are translation. And you can imagine that just keeping on this plane, because you understand that we can work in 3D dimension, but just staying in 2 dimension, we see 3 examples, and you can imagine something. That this movement, as I represented here, is related to the direction of the force. So you see that I have represented a force, which is a vector, and having a line of action passing through the CR, the center of resistance, which is this blue point that I've been drawing there, and the movement of the center of resistance is happening along the line of action of the force. The movement of all other points is happening along parallel lines. So this is the translation. And you can have a different translation if you change the direction of the force. So if you apply force with this different direction, you will have a different translation. So the CR will move like that, and all the other points will move along different lines. Okay. So translation is not a movement, this is a big family. And what is rotation on the other hand? Rotation in a two-dimension is a movement where the center resistance is staying exactly where it is, while all other points of the rigid body, which is the tooth, are rotating around the CR. In other words, the pure rotation is not moving the mass of the tooth. It's not a real displacement, it's just a change in the position around the center of resistance. These are two extreme movements, and let's say again that in 2D dimension, we have only two possible directions of rotation that we usually call clockwise and counterclockwise. This is true that we only have two directions if we see things in a 2D dimension, in a 2D world. But in 3 dimension, actually what we do is that what is usually done by the computer is that we identify a single plane in a sphere where this rotation happens. So you can imagine that the rotation, of course, it's on one plane can be only clockwise and counterclockwise. But when we think to the rotation in 3 dimension, we first identify one plane in 3 dimension that is not necessarily the front, sagittal or occlusal view, but any intermediate plane. It can be a plane that's being like this, is rotated somehow, and we identify a rotation happening in that direction. That's quite complicated to visualize and also to compute, but for us it's better that we stay with this. So on this plane we had this rotation that can be clockwise or counterclockwise, and we analyze things on another plane. And then there are combined movements. As a matter of fact, it's not very often that we have a movement which is a pure translation or a pure rotation. Yes, we can get it, but usually the great majority of the movements that we want, or that we actually deliver, are combined movements, where there is a part of translation and a part of rotation. Here in this diagram, you see this represented as a movement that goes up from the first step of translation, so the tooth moves from here to here. So look at the incisor point. Goes here. The center resistance goes here. And this is a translation because you see all points are moving along parallel path. And then it's represented with the second stage where the tooth is rotating around the center rotation. So this is the rotation, and this is the rotation. This is the angle of rotation. This is just a representation where we imagine that the movement is done in 2 steps. First the translation, and then the rotation. And this leads to a displacement. But I need to make one thing very clear. We can go from position 1, that is this one, to position 3, that is this one here, through many different paths. Okay? Some paths are longer, some paths are shorter, and there is only one that is the shortest, of course. And what would you like to use? The longer or the shortest path? You need to choose from position 1 to position 2. I mean, when you had to go from Santiago to Concepcion, basically the only 2 cities in Chile, you don't pass through, let's say, Rio de Janeiro, isn't it? So the reason is that one thing is to define the displacement as a whole, but it's also important to define the path of the movement. And we should always try, at least try, sometimes we're not so good, but this should be our goal, to follow the shortest path. And, go back here, the shortest path is defined by the center rotation. So the shortest path to go from position 1 to position 3 is not to make, for example, first a translation and then a rotation, but it's to combine these two movements at the same time so that it's, the movement can be represented by a progressive rotation around the point which is here. So what is the center rotation? The center rotation is a way to describe mathematically a path of movement. The displacement, it's the representation of the initial and final position. So what we're looking at, we are trying to get the displacement that we need using the shortest possible path. So identifying the center rotation. The displacement itself is not identified by the center rotation, because I want you to understand that we can go on with this rotation from point 1 to 3 to another point 4 that can be here. So if we can do a rotation like that. So this is another thing, but this is the shortest path. And this center rotation is related to the force system. So what we are looking at from now, it's a relation between this point, that is the center rotation, and that represents a path of movement, and the force system. Okay, force system that, as we say, is described in before as the force, the moment, and the moment to force ratio. I don't like very much the old description of the typical movement. I mean, when I was studying biomechanics, in Aarhus, in the syllabus, we had this, okay, look, these are the force systems that we can get. This was taken by old papers, also by a person, where he was talking about, let's see if I have to draw it. He was talking about what he was calling uncontrolled tipping that was happening when you were applying the force at this level, and the center rotation here was in this area. Or controlled tipping, if you could apply the force at this level, and the center rotation is in this area. Translation, when the force was applied here. And what was called root movement, with the force that was applied above the CR, where the center rotation was more or less here. But these are just few examples that cannot cover the reality. So what does it, how do we represent the movement where we, just to stay on this plane, because as we say, the reality is more complex because it's a solid board, but just to stay in two dimensions, how do we represent a movement where a vertical displacement has also to be added? In other words, here we are having 4 conditions with center rotation that are one here, this is at infinity, and and this is here. You can imagine that there are many other possibilities of moving the teeth. And how many are there? You can have a center rotation in any point here around, and all these points, this seems to be a sort of sickness. And every point represents a different movement, where you are having also not only transverse sagittal force, but also a vertical force. And this is only one plane. Now, imagine how are things in 3D. Okay, our patients are all 3D. I've never been working on a cartoon. And